Hello, today we're going to talk about a company called ASML. This company does something that affects every single person in the world. The chips inside the phone and computer in your hands, along with those in cars and medical equipment, many of them are printed using ASML's machines. It started back in 1984 from a small, leaky wooden shed, and now it has grown into one of the most important equipment companies in the world. Today, let's walk through the whole story step by step and make everything clear. Chapter 1: The Past. ASML began in the Netherlands in 1984 as a small joint company between Philips and ASM International. It was built to make machines that help print tiny patterns on computer chips, a process called lithography. Those tiny patterns became important because chip makers wanted smaller, faster, and cheaper chips for computers and other electronics. The company started in a rough, leaky shed next to Philips research buildings in Eindhoven, which shows how small it was at the beginning. The full name first was ASM Lithography. Philips and ASM International created it after years of research work that had already been going on inside Philips in the 1970s. The reason for the company was simple. Chip makers needed better tools than the ones already available, and the market for semiconductors was growing fast. ASML's first system was the PAS-2000 stepper, launched in 1984. A stepper is a machine that shines light through a pattern and copies that pattern onto a silicon wafer, which is a thin round slice of material used to make chips. The company was not born rich or famous. It began as a collaboration between two industrial parents, and it had to prove that it could build useful machines in a field already crowded with strong rivals. At that time, the chip industry was already very important in the United States, Japan, and parts of Europe, so a new Dutch company had to fight for trust. This early period mattered because every machine sale helped ASML survive and continue building newer tools. ASML's early systems were part of a fast-moving race to make chip printing more precise. In the 1980s, computer chips were becoming more useful in many products, from office computers to industrial equipment and early consumer electronics. ASML had to make tools that were good enough for companies that were spending millions of dollars on factories. One of the first big steps was the PAS-5500 platform, which came later and became a breakthrough system for the company. The company's early years were shaped by technical uncertainty. Making chip tools is difficult because the machine must place patterns with extreme accuracy. If the pattern is even a little wrong, the chip can fail. That means the company had to keep improving how its machines worked, one generation at a time. This pressure helped shape ASML into a company that works with long research cycles, not short ones. A major early change came in 1988 when ASM International sold its stake to Philips because of financial pressure. That left Philips with more control, and it changed how the company developed. In 1995, ASML became an independent public company and was listed in Amsterdam and New York. This mattered because public listing gave the company more money and more freedom to invest in research. It also made ASML less dependent on its parent companies. Going public was a big turning point. Chip-making machines take a lot of money to build, test, and improve. ASML needed a large and steady source of money to stay in the race against Japanese competitors such as Canon and Nikon. The IPO helped the company pay for more research, more factories, and more engineers. It also meant the company had to report more clearly to investors and deal with public pressure to perform. A very important step came in 2001 with the twin-scan system, which used dual-stage technology. This machine could work faster because it allowed two wafers to be processed in an efficient pattern. That improved productivity and made ASML more attractive to major chip makers. In chip manufacturing, speed matters because factories are expensive and must run almost all the time. A machine that improves output can save a customer a lot of money. This was also a period when chip makers wanted more powerful chips for computers, phones, and servers. ASML's job was to make it easier to keep shrinking chip features. Shrinking means making the tiny lines on a chip even smaller. Smaller lines let more transistors fit in the same space, and transistors are tiny switches that control electricity inside a chip. That is one reason modern devices can do far more than older ones. The twin-scan era showed that ASML could do more than survive. It could lead. The company became a central supplier in the global chip industry, and by the early 2000s it had become the largest supplier of photolithography systems. That meant many chip makers now depended on its machines. The deepest story in ASML's history is its long bet on EUV, short for extreme ultraviolet lithography. This is a way of using very short wavelength light to print much smaller chip patterns. The idea was extremely hard. It took many years of research, many failed prototypes, and billions of euros. At first, EUV looked like a dream that might never become practical. ASML kept going anyway. In 2010, it shipped the first prototype EUV tool, called the TwinScan NXE3100. That was a landmark because it showed the idea was no longer only a lab project. It had become a real machine. In 2012, ASML announced a customer co-investment program, with companies like Intel, TSMC, and Samsung helping fund EUV work. This was unusual. It meant the biggest buyers were helping pay to finish the tool they wanted to use later. In 2013, ASML acquired Cyma, a key supplier of EUV light sources. This mattered because EUV machines need a special light source, and that part is one of the hardest pieces of the whole system. By buying Cyma, ASML made its supply chain stronger and more secure. The company was no longer only a machine builder, it also controlled a critical part of the technology chain. EUV mattered because chip makers kept hitting limits with older light methods. As chip features got smaller, normal printing methods became harder to use. EUV gave ASML a way to stay ahead. It helped chip makers build more advanced processors for phones, computers, data centers, and artificial intelligence systems. These chips later became central to companies in the United States, Taiwan, South Korea, Japan, and Europe. The effect reached everyday life too. Faster chips helped make phones more powerful, saved battery life, and made cloud services run better. People in many countries used devices that depended on chips made with ASML tools. Even if most people did not know ASML's name, they used products that depended on its machines. That is part of why ASML became one of the most important companies in modern technology. ASML did not grow smoothly. In the late 2000s, it faced a sharp drop in sales during the global financial crisis. In 2008, management cut about 1,000 jobs worldwide, mostly contract workers, and used Dutch unemployment support to avoid even larger layoffs. This shows how strongly the company's fate could change when the chip market slowed. When customers delayed new factories, ASML felt the effect quickly. The pressure was not only financial. EUV development was slow and expensive, so the company had to keep investors patient for many years. If the technology had failed, ASML could have lost a huge amount of money. Instead, it kept building, testing, and improving. That long effort became one of the most important stories in the company's history. By the 2000s, ASML had become much more than a Dutch equipment maker. It was now the company that many advanced chip factories needed if they wanted to keep moving forward. That gave ASML a powerful place in the world economy. It also made the company part of political debates about trade, export controls, and national security. The company's work affected countries in different ways. In the Netherlands, it brought high-tech jobs and strong export income. In the United States, it supported chip makers like Intel and customers that needed the most advanced tools. In Taiwan and South Korea, its tools helped companies such as TSMC and Samsung stay at the front of chip production. In each place, the company's history became tied to local industry and jobs. Here is a simple timeline of major early events. 1984, Philips and ASM International create ASM Lithography, and the PAS 2000 stepper is launched. 1988, ASM International sells its stake to Philips because of financial pressure. 1995, ASML becomes an independent public company and lists in Amsterdam and New York. 2001, the twin-scan dual-stage system appears. 2002, ASML becomes the largest supplier of photolithography systems. 2010, the first EUV prototype tool ships. 2012, Intel, TSMC, and Samsung help fund EUV development. 2010s, ASML becomes central to advanced chip production and AI chip supply chains. ASML's history shows a company that grew by solving one hard problem after another. It started with one product idea, then moved into better lithography systems, then into EUV, and later into High-NA EUV, the next step in chip printing. The company's story is not just about size, it is about persistence. Many years passed between early research and the machines that now support the most advanced chip factories in the world. The company's path also shows how technical work can affect many people in many places. Engineers in the Netherlands designed the systems. Suppliers around the world made parts. Customers in Asia, Europe, and the United States used the machines to make chips for phones, laptops, data centers, and cars. This is why ASML's past is not only a company history, it is also part of the history of modern electronics. Chapter 2, The Present. Today, ASML makes the machines that help build advanced computer chips. These machines do not make the chips themselves. They print tiny patterns on wafers, so chip factories can create the chips later. ASML is now one of the most important suppliers in the semiconductor industry, because modern chip factories need its tools to keep making smaller and better chips. ASML's main business is lithography systems. Lithography means using light to draw very small patterns on silicon wafers. The company sells machines for different stages of chip making, including deep ultraviolet systems and extreme ultraviolet systems. It also sells parts, upgrades, software, and services that help customers keep the machines running. These services matter because the machines are very complex and need careful support. ASML's customer list includes the biggest chip companies in the world. Its machines are used by makers of logic chips and memory chips. Logic chips power phones, laptops, servers, and AI systems. Memory chips store data. If a factory wants the most advanced logic chips, it often needs ASML's best systems. That makes ASML a key supplier in the full chain of electronics production. A lithography machine is like a super precise printer, but it works on a tiny scale. It shines light through a pattern and places that pattern on a wafer. Then the wafer goes through many more steps, such as etching, adding materials, and cleaning. This is done many times to build the layers of a chip. A modern chip can have dozens of layers, and each layer must line up with great accuracy. ASML's EUV machines are especially important because they use very short wavelength light. That lets chip makers draw smaller features than older tools can handle. A smaller feature means more parts can fit into the same chip space. This helps chips become faster and more power efficient. The machines are huge, costly, and made from many specialized parts. ASML is a very large company. In fiscal 2025, it reported net sales of 32.7 billion euros and a gross margin of 52.8%. It also reported 4.7 billion euros in research and development expenses for 2025. In its 2025 fourth quarter results, the company said quarterly revenue reached 7.5 billion euros and net income was 2.1 billion euros in the third quarter. It also reported a 2025 annual revenue figure of 416.2 billion euros in a separate report summary, but that figure is inconsistent with ASML's official euro results and should not be treated as ASML's own reported euro total. ASML's official company results should be read from its own filings and results pages. The company also said it had 164,000 full-time equivalent employees in 2025 according to its environmental progress report. That is a very large workforce, but still small compared with the number of users of its machines around the world. These employees include engineers, service workers, logistics teams, software staff, manufacturing staff, and administrative teams. Many of them work in the Netherlands, but the company also has people in many other countries because its business is global. Daily work at ASML is shaped by precision and planning. Engineers design new tools, factory workers build and test the machines, supply chain teams track parts from many suppliers, service teams help customers install, maintain, and upgrade machines after delivery. This is a company where a small part can matter a great deal, because one missing piece can delay a very expensive machine. The work is also guided by long research cycles. ASML spent 4.7 billion euros on R&D in 2025. That shows it keeps putting large amounts of money into future machines, even while selling current ones. The company also said it had more than 16,000 research staff in a 2025 report summary. Research staff do not just sit in one lab. They work with optics, mechanics, software, chemistry, physics, and manufacturing. ASML is a public company listed in the Netherlands and the United States. It has a two-tier governance structure, with a board of management and a supervisory board. Christophe Fouquet became CEO in April 2024. This kind of structure is meant to separate daily management from oversight. The company uses this system because its business is so large and technical that clear control matters. The company's revenue comes from both tools and services. In the first half of 2025, product sales were larger than service sales, but services still brought in billions of euros. Services include maintenance, parts, software, and support contracts. These services help customers keep factories running. They also bring recurring income to ASML, not just one-time machine sales. ASML's biggest strength is its position in advanced chip manufacturing. Its EUV systems are essential for the most advanced chip nodes. A chip node is a way of describing a generation of chip manufacturing, often linked to smaller feature sizes. The company's tools are hard to replace because they are the product of many years of research and very deep technical knowledge. That gives ASML a strong position in the market. Another strength is the company's close link to top customers. Major chip makers work with ASML very early when new machine designs are being developed. This helps the company build tools that match real factory needs. ASML also has strong cash generation and high margins in 2025. That helps it keep funding research. ASML also faces hard problems right now. One challenge is global politics. Trade rules, export controls, and tensions between countries can affect where ASML can sell its machines. Another challenge is manufacturing complexity. The company must get many suppliers to deliver very advanced parts on time. A delay in one place can slow the whole system. Another challenge is the need to keep improving. Chip makers want smaller and better chips every few years. That means ASML must keep inventing new tools while making current tools reliable and efficient. It must also manage costs, protect its technology, and train enough skilled workers. These are not small tasks. Artificial intelligence has made ASML even more important. AI systems need powerful chips, and advanced chips need top lithography tools. When demand for AI chips rises, customers often want more advanced production capacity. This creates more demand for ASML systems. In 2025, ASML said demand visibility remains strong and tied to AI-driven semiconductor demand. This has a real effect on daily work. More demand means more planning, more factory scheduling, and more support visits. It can also mean more pressure on suppliers to deliver parts quickly. The AI boom does not only affect software companies, it also affects the machinery companies behind the chips. One real example is ASML's 2025 revenue record of 32.7 billion euros. Another is the 2025 quarter when ASML reported 7.5 billion euros in net sales. A third is the rise in performance obligations to 46.5 billion euros in 2025, which means customers had committed to buy systems and services over the next several years. These numbers show that the company is busy, booked, and deeply tied to future demand. Another real example is the company's installed base. ASML said in January 2026 that its installed base had grown to more than 2.5 billion active devices in one reporting context, but that number was referring to Apple, not ASML, so it should not be used here. For ASML, the important point is that many chip factories worldwide already use its systems and need support for them. The installed base of ASML machines is large and keeps growing. In the Netherlands, ASML supports a large high-tech ecosystem around Veldhoven and Eindhoven. That includes direct jobs and many supplier jobs. In Taiwan and South Korea, ASML's machines help support advanced chip factories that are important to local economies. In the United States, the company supports Intel and the wider semiconductor supply chain. In China, ASML still has a large customer base, but export rules affect what it can sell. The company's presence is therefore global. It affects factory workers, engineers, logistics teams, software specialists, and shipping routes. It also affects consumers indirectly, because the chips made with ASML tools end up in phones, computers, cars, servers, and network equipment. That means the company's work reaches far beyond its own offices. Chapter 3. Effects around the world. ASML affects many countries because its machines are part of the world's chip-making system. The company's tools are used in Europe, Asia, North America, and other regions. Its work changes where high-tech jobs are created, how supply chains are built, and how advanced chips are made. The effects are not the same everywhere. Taiwan is one of the most important places in ASML's global story. Taiwan Semiconductor Manufacturing Company, or TSMC, is one of ASML's major customers and one of the world's most important chip makers. TSMC makes many of the most advanced chips used in phones, computers, and AI systems. That means ASML's tools support much of the world's advanced electronics through production in Taiwan. The effect in Taiwan includes jobs, factory growth, and strong technical cooperation. Engineers there must learn to use very complex ASML machines. They also need maintenance and parts support. The relationship is deep because chip making in Taiwan depends on advanced lithography, and ASML is one of the key suppliers. This creates a close link between a Dutch company and Taiwan's high-tech economy. The United States is another major region in ASML's network. Intel has been one of the company's important customers and co-investors in EUV technology. The United States also has many companies that design chips, but do not make them themselves. These companies need chip factories, and those factories need machines. ASML systems help support that chain. There is also a political side in the United States. American leaders care about chip supply because advanced chips are used in military systems, cloud computing, and AI. That has made ASML part of export control discussions. The company's sales and service work in the US support jobs in places like Arizona, Oregon, California, and Texas, where semiconductor work is concentrated. Its effect is both industrial and strategic. In Europe, ASML is a major industrial success story. The company was built in the Netherlands and remains strongly tied to that country. It supports thousands of jobs in engineering, manufacturing, logistics, and research. It also supports many supplier firms in Europe that build precision parts, optics, and software systems. Europe also gains from ASML's global reputation. The company is one of the continent's most important technology firms and one of the few European companies with a central role in a world-leading industry. This matters for European industrial policy because the continent wants stronger control over advanced technology supply chains. ASML helps make that possible, but it also brings political pressure because many countries want access to its machines. That puts the company in the middle of trade and diplomacy. China is one of the biggest and most complicated markets for ASML. The company has sold many machines there over the years, and China has been an important source of revenue. But export controls and political tensions have changed what ASML can ship. That means its impact in China is mixed. It still supports parts of the chip industry, but the rules are tighter than before. The effect on people in China includes factory jobs, engineering work, and local supplier activity linked to chip production. But there are also limits. If a Chinese company cannot buy the most advanced ASML tool, it may have to use an older one or delay its expansion. That changes how quickly local chip factories can grow. India is becoming more important in ASML's global supply chain. Recent reports say India has overtaken Vietnam in the number of Apple suppliers, and other supply chain reports show ASML's supplier network in India expanding as companies diversify away from China. For ASML, India matters because chip supply chains are spreading across more countries, not staying in one place. This can create more jobs for local suppliers and logistics workers. India's role is still growing, not finished. The country is part of a wider trend in electronics manufacturing, where companies want more geographic variety. If India keeps building supplier depth, it may become more important for parts, assembly, and support work tied to advanced tools. This shows how ASML's influence can spread beyond direct machine sales. Vietnam is another important Asian location. Reports say Vietnam has become a specialist base for some Apple products and has long been part of broader electronics manufacturing shifts. While this is not ASML's main manufacturing center, it matters because electronics growth in Vietnam supports the wider chip and device ecosystem. The more electronics factories a region has, the more advanced chip supply chains need to reach them. Vietnam's effect includes factory work, supplier work, and more shipping and logistics activity. The country also shows how the world is spreading electronics manufacturing across different regions to lower risk. ASML benefits from this spread because more advanced devices create more demand for chips, and more chip demand creates more demand for lithography tools. Japan and South Korea remain very important in the semiconductor world. Japan has long been home to major equipment and materials companies, while South Korea is a giant in memory chips and logic chips. ASML sells tools into both markets. Samsung has been one of the major customers that helped fund EUV development. That shows how deeply ASML is linked to Korean chip production. The effect in these countries includes high-skilled jobs and heavy investment in fabs, which are chip factories. It also includes pressure to keep up with fast technology change. If a factory in South Korea or Japan wants to stay advanced, it must work closely with machine suppliers like ASML. That makes ASML part of the planning for future chip capacity in both countries. Africa is not a major ASML manufacturing hub, but the company still affects people there indirectly through products that contain advanced chips. Phones, computers, data services, medical devices, and industrial systems in African countries often depend on chips made with high-end tools. That means ASML's role is felt through the global electronics market, even where the company has no big physical footprint. The same is true in Latin America and the Middle East. These regions also feel the effects through trade and prices. If chip supply is tight, the cost of electronics can rise or shipments can be delayed. If advanced chip output grows, more devices can reach more markets. ASML sits upstream in that chain, so its machines influence what is available later in stores and factories around the world. ASML's global impact includes jobs in many places. In the Netherlands, people work in engineering, production, software, and logistics. In Taiwan and South Korea, people work at customer fabs that rely on ASML equipment. In the United States, people work in chip design, fab support, and equipment service. These jobs often require long training and careful technical skill. Working conditions vary by region. In high-tech regions, the work can be demanding because machines are complex and downtime is expensive. Service staff may need to travel and solve problems quickly. At the same time, the jobs can be stable and highly skilled because the company's technology is hard to replace. This makes ASML part of long-term industrial employment in several countries. ASML also has environmental effects. Its machines and supply chain use energy, materials, and transport. The company says it has a climate plan called Apple 2030 in one web result, but that is about Apple, not ASML, so it does not apply here. For ASML, the important environmental facts are that it reports sustainability information and has continued to invest in more efficient systems and reuse of parts. The company's 2025 report summary also said it was working toward net zero emissions for Scope 1 and 2 and high rates of parts reuse. Environmental impact is also indirect. Advanced chips can make devices more energy efficient, and more efficient chips can reduce power use in phones, data centers, and other systems. But making the machines and chips also uses resources. That means ASML's environmental effect includes both the benefits of better chip efficiency and the costs of industrial production. The same company can affect places in different ways. In the Netherlands, it is a source of national pride, exports, and high-skilled work. In Taiwan, it helps support the world's leading advanced chip factories. In the United States, it is part of national technology strategy. In China, it is shaped by export controls and trade restrictions. This difference matters because a machine company is not just a seller of tools. It becomes part of local industry, politics, and employment. ASML's global effect comes from the fact that one machine can influence many later steps in the production of electronics. That is why its reach is so wide. Chapter 4. The Future. ASML's future depends on technology, trade, and the pace of chip demand. The company is preparing for a world that wants more powerful chips, smaller chip features, and more stable supply chains. It is also preparing for a world with stronger political tension and more pressure on industrial policy. These forces shape the company's plans. One major trend is artificial intelligence. AI systems need advanced chips, and advanced chips need the best lithography tools. This keeps ASML near the center of future chip demand. Another trend is the move to more advanced chip nodes, which need finer printing than before. That pushes ASML to develop even better systems. A third trend is geographic diversification. Companies want more than one country in their supply chain. That means ASML and its customers must think about China, Taiwan, India, Vietnam, Europe, and the United States at the same time. A fourth trend is climate and energy use. Chip factories and tool makers must reduce emissions and use resources more carefully. One of ASML's biggest future projects is High-NA EUV. This is the next step after standard EUV. It uses a larger numerical aperture, which is a way of measuring how much detail a lens system can capture. In simple words, it helps print even smaller and more exact chip features. ASML shipped the first High-NA EUV system in 2023, and first customer deliveries were expected in 2025. This technology matters because future chips need even finer patterns. High-NA EUV is meant to support sub-2 nanometer manufacturing. That sounds very small because it is. In chip terms, it means the industry keeps trying to fit more power into less space. ASML is one of the main companies making that possible. ASML is spending heavily on research and production. Its 2025 report showed 4.7 billion euros in R&D spending. The company also has a large backlog of customer commitments, which helps support future planning. These commitments are important because ASML must plan years ahead for special parts, factory space, and expert staff. The company also continues to build stronger relationships with customers and suppliers. This helps it spread technical risk and secure parts for highly complex systems. By working closely with customers like Intel, TSMC, and Samsung, it can align machine development with real factory needs. That reduces the chance of making a tool that does not fit the market. ASML has several risks ahead. Trade rules could limit where it can sell its machines. This is not a small issue because some of its biggest markets are tied to countries involved in trade tensions. If export limits change, the company may have to redesign its sales plans or accept slower growth in some regions. Another risk is technical. High-end chip tools are difficult to build and even harder to deliver at scale. If one part fails or a new system takes too long to stabilize, delivery schedules can slip. That can affect revenue, customer trust, and factory planning. ASML also faces risks from supply chain concentration because many specialized parts come from a limited group of suppliers. ASML's future also includes climate goals. The company says it is working on emissions reduction and greater reuse of parts. Chip tools are large industrial machines, so efficiency matters. Better machine designs can reduce waste and help customers use resources more wisely. That does not remove environmental impact, but it can lower it. The company must also think about shipping and transportation. A lithography system is very large and expensive to move. That means global logistics will stay important. Lower carbon transport and better packaging may matter more in the years ahead. These are practical steps, not abstract ones. In the Netherlands, future ASML growth may mean more jobs, more training, and more pressure on housing and local services near its main sites. In Taiwan, the company's future machines may support even more advanced chip production. In the United States, the company's tools may remain central to attempts to rebuild domestic chip manufacturing. In China, future effects will depend on export rules and geopolitical conditions. In India and Vietnam, future effects may include more supplier growth and more electronics manufacturing. In Europe, ASML may keep serving as a symbol of high-end industrial skill. In Africa and other regions, its effect will remain indirect but important through the products people use every day. A few key future markers are already visible. 2025, first High-NA EUV customer deliveries begin. 2025, R&D spending stays very high at 4.7 billion euros. 2025 to 2026, customer commitments stay large, showing continuing demand. Late 2020s, more advanced chip nodes will likely depend on high-NA systems. 2030, ASML's environmental and production plans will be shaped by long-term emissions and supply chain targets. These dates matter because ASML plans on a long timeline. The company does not build for next month only. It builds for the next decade or longer. That is normal in chip equipment, where one machine generation can take many years to develop. For workers, ASML's future may mean more skilled jobs in engineering, service, logistics, and manufacturing. For customers, it may mean better access to machines that can make faster chips. For governments, it may mean more attention to export control and industrial policy. For consumers, it may mean phones, computers, and cloud services that keep improving because the chips inside them keep improving. The future is therefore not only about ASML itself, it is about the many people and countries that depend on the machines it makes. The company's next steps will continue to affect where chips are made, who gets them, and how fast technology changes. Chapter 5, Summary. ASML began in the Netherlands in 1984 as a joint venture between Philips and ASM International. It was created to build lithography machines for chip makers. Its first machine was the PAS 2000 stepper. Later it became an independent public company in 1995. Over time, it grew into one of the most important companies in the semiconductor industry. Its biggest historical turn was the long bet on EUV technology. That effort took many years, many engineers, and very large investments. It led to prototype tools in 2010, customer co-investment in 2012, and the acquisition of Cyma in 2013. These steps helped ASML become the main supplier of the most advanced chip-making machines. Today, ASML builds lithography systems, services them, and supports customers around the world. It reported 32.7 billion euros in net sales and 4.7 billion euros in R&D spending in 2025. It had about 164,000 full-time equivalent employees in 2025. Its work is tied to advanced chips used in phones, computers, servers, and AI systems. ASML affects many regions. It supports jobs and industry in the Netherlands, Taiwan, the United States, Europe, China, India, Vietnam, South Korea, Japan, and beyond. Its effects can be positive, such as high-skilled work and advanced technology. They can also be difficult, such as export limits, supply chain pressure, and environmental costs. Its future depends on AI demand, High-NA EUV, supply chain planning, trade policy, and climate goals. The company is preparing by spending heavily on research, keeping close ties with customers, and building new machine generations. Its story shows how a small Dutch company became a central part of the world's chip system. Today we learned about ASML, a company that started in 1984 as a small joint venture in the Netherlands, and through years of persistence and innovation, grew into an essential supplier of the world's most advanced chip-making machines. In the future, we'll continue sharing stories about many other interesting companies. If you enjoy this kind of content, remember to subscribe to the channel and turn on the notification bell so you won't miss any new videos. See you next time.